Hello, this is my cat, Diego, and today I chat with Kanjun Qiu. Kanjun is really sharp and leads an AI company, and as part of What Information Wants, I'm doing this series now to understand, is there a third replicator? There's genes, and then there's memes. Are there these like computer memes, these chemes? And so her and I chat about that and learn about their really fascinating take on AI with her company, Generally Intelligent, where they try to get the AI to understand very specific forms of how humans learn. So it tries to teach the AI, or the AI tries to learn itself, things like object permanence and things that us as little kids know, and then using that as a building block then to learn other kinds of more general and generally intelligent behaviors. It's a fascinating conversation, and I hope you enjoy it. Thanks.
Hello, listeners. Welcome to the Rhys Show. I am Rhys, the co-founder of Root, and this is my world. We're in real life today, which is great. And I believe that this century is a turning point in human history, and I'm here to help you navigate it. I hope you come away with a new understanding of the scientific, technological, and societal trends that are poised to radically reshape our world, and how you can work with those trends to become a live player in building a solar punk future. So, to chat about all those amazing things, today I'm excited to chat with Kanjun Qiu. And Kanjun is this amazing community builder in SF. We're currently in SF. And she's the CEO of Generally Intelligent, which is an org that's creating artificial general intelligence, aka AGI, by building machines that learn the way humans do. Kanjun, thanks for being on the show and welcome.
Thank you.
Excited to dive in. And as a side note, maybe we'll get to this at the end, but yeah, like Kanjun, I met Kanjun when I went to her first house, the archive in San Francisco. And I was thinking about when I first moved to San Francisco, and I'm not sure if you remember this, Kanjun, and you were very welcoming and you were showing me all the house. But the room that you all had available was like the Harry Potter room under the stairs.
The Harry Potter closet.
And I looked at it and we were looking at it and it was like, it was still like $600 or whatever. And I remember like fitting I'm 6 feet tall or whatever. So my body could fit. But I remember, and I had people take pictures of me and I was like, I just don't think this is good for me or my dating life. So thank you for the offer.
Agree with that. I would agree. I think actually we stopped renting out the Harry Potter closet because one, it seemed a little bit dangerous. You know, there's not very much ventilation in the closet under the stairs. But also we ended up getting all 3 floors of the house and it ended up being 25 people. So that was a lot.
Yeah. You didn't need to shove more people in all the corners.
We don't need to shove more people in the corners.
That's funny. So I think we'll chat maybe about like some of your other, because Kanjun has all these diverse interests, which is great. But I think we're going to spend most of the day talking about AI.
Yes, which is my primary focus and interest.
Yes, great. And so I think that for me, I'm kind of a noob with AI. I know computer science kind of, but I didn't take any classes on it, surprisingly. And I'm trying to understand, like the background here that we chatted about beforehand is that I'm writing this book on what information wants and how genes create the tree of life and how memes create the tree of ideas. And now we have this new, possibly scary thing, artificial intelligence, and maybe it's a third replicator and blah, blah, blah. So that's kind of the space that we'll be exploring. But before we go and do all that, can we start with your company and what it is to build, why you're building machines and starting with like the human side of things, or tell us more what that means.
What do we do?
Yeah, exactly.
So Generally Intelligent is an AI research company. And we, the way to think about it is we're trying to build human-like general intelligence. And what I mean by human-like is we want a system that can learn the kinds of things that humans can learn using a similar amount and type of data to what humans use. And so, evolution used a lot of data, training data, to produce the human brain core architecture. And so there's that training stage, which is something that we, right now we train these large models and we use a lot of data to train things. But humans also have a learning stage. This learning stage is really important. It's humans are remarkably general in what we're able to learn, the types of environments we're able to adapt to, the types of problems we're able to solve. And machines, after this training stage, are not. They're not general. And, they're becoming more general. There are these language models that are a little bit more able to kind of handle different situations. But primarily, they're not general in the same way, in the sense that they don't really learn new things in the way that humans learn new things. To retrain these systems today takes a lot of data. There's no idea of learning. You can show a person, you can tell a person once, like, don't insult people.
Yeah.
And they'll be like, okay, done.
Yeah.
I'm not going to
Yes,
insult
ma'am.
people.
Yeah, exactly.
Or like, don't, always cut out your recycling before you put it in the bin.
Or else you're causing climate change. Exactly.
Exactly. Which is a notice that we got this morning.
Nice.
And we're like, okay, we will do that.
Yes.
But you would have to tell this machine learning model, many, many, many times, tens of thousands of times. So building human-like general intelligence, why is that important? Like, you might be able to say, oh, well, it doesn't matter. Why don't you just use tons of data to allow these models to learn on an ongoing basis? And there are really two reasons why you'd want to, be able to learn on an ongoing basis. One is there are a lot of things that humans do that don't where there's just not enough data to teach us. So there's this kind of like long tail of everything. And these systems today, we're not really good at dealing with the long tail of everything. The second reason is actually a little bit more about safety and kind of deployment. So, I think a lot about what is the impact of AI, of general intelligence on humanity. And there are all of these kind of like stories of paperclip maximizer and things like that. And I think those are, good things to think about. Like, we should think about how to align AI with what humans want. But, I ran an AI recruiting company before this. And one thing that I learned is customers do not buy an AI that does not do the thing they want. And so capitalism really pushes us to solve the alignment problem. Because it's really annoying if your thing keeps doing something that's not what you asked it to do. Now, there's things like deception and things like that. So, of course, alignment is a real problem. But I think there's also, secondly, kind of an important deployment problem. If you think about what does AI give us, like what's the impact of that on the world? What it gives us is humans who have substantially more capability than they did before, individuals who have substantially more capability. And so now you want to start thinking about, okay, what's the impact of that on the world? One potential impact is, for example, totalitarian governments are much easier to sustain. If you have substantially more capability and you deprive other people of general intelligence, then you just have like much more power. And the power imbalance, to me, I think that's quite brittle. Like, it's not robust to have an ecosystem where certain individuals have substantially more power. And so what I'm interested in is, this human-like intelligence, something that is able to learn and be easy to train. My hope is that this will allow AI to be much more democratized. And, the current large systems, that's not necessarily going to be true. So, okay, what do we do?
Wait, and let me pause you for a second before you go into it, which is that, so this is helpful to think, I like the frame of, that it was a lot of training data in order to get humans. I mean, we had 4 billion years, we had all the life, and then we blah, blah, and then we got plants and animals, and then we got the chimps, and then we got brains, and then we got human brains, and now, and then as you say, there's both we were trained, but then there's the learning side too, where it's like, we were trained, and then we pop out and we know very little, and anybody could come and do bad things to us. And then over time we get much better, and we get better at learning things.
That's right.
And you and I can learn today. And then I guess the other piece here that I hear what you're saying about the long tail bit, which is, you don't necessarily want, not all of reality has tons and tons of data. And so you might want to show only one cat to the AI and for it to be like, that's a cat.
One specific example of this is, or like some examples of this are like, you might want a salesperson to learn how to do sales at your company. And that particular sales process is like really specific to your company. You don't have 85,000 examples of sales manuals. You have one. So you would like a human to be able to come in and learn how to do sales at your company, or learn how to do things specifically the way that you want them to do things. And it's just kind of in the paradigm that we currently think about intelligence or training these large models, or small models. It's train and test. And so you train a model, then you test it, and now during test, it's basically doing the task.
Okay.
But humans are train, as in evolve, and then learn, and then do the task.
Okay.
Right? So there are kind of these 3 stages.
Interesting.
Yeah.
Interesting. And so, so that gets to maybe, and before we get into that for a second, it's like, I think the democratized thing, I like that a lot more. Hey, who doesn't like to democratize stuff?
I think it is dangerous.
It's dangerous. I think that there's a question, at the end of Bostrom, superintelligence, whatever he talks about, different kinds of situations that could occur, and multipolarism is one of them. And I think that some kind of like multipolar, my intuition, knowing very little about it, is maybe similar to yours, which is that having some kind of quick feedback loop between our values and the machine values and whatever, and having those things be in this complex multipolar ecosystem with a lot of actors kind of and agents balancing each other feels like a slightly safer scenario than like, okay, we're just going to make one really big model and hope it works.
Yeah.
You know what I'm saying?
Potentially. Yeah. I think, I think, I guess no one really knows the answer. My current thinking on it, and this might change over time, so disclaimer. But my current thinking on it is so it's much easier to destroy than to create. You also, coordination is really important. Yeah. And so, okay, in the first situation, it's much easier to destroy than to create. What we have today is people who want to destroy. It is hard for them to recruit other people to their cause because most people don't want to do the same thing. And that is a nice, natural balancing factor. And other people are trying to prevent them from destroying things. Yeah. And so there's enough kind of force preventing destruction. And it's also hard for the destruction to get power. But in a situation with AI, like you could replicate this AGI many times and then use that to destroy. It's like easier to accumulate resources toward destruction. Yeah. And so maybe one way to kind of help balance that out is to have many more people who have, kind of naturally, who don't want to be as destructive and who are able to like use many more resources toward preventing the destruction. Another potential solution, like there are a lot of, potential things that might make a little bit of progress here is like help everyone be less traumatized and recover from their trauma so that they have less tendency to want to destroy things. Yeah, we were just talking about childhood and going to therapy and stuff beforehand. Right. Exactly. Yeah. So that's like another thing that can be done in parallel.
But I like the idea of that you can either add, it's easier to destroy than create. And so you need to add friction around the destruction, either the friction to coordinate, you need to add more friction to coordinate, or you need to make it, even if you have the ability to coordinate, you need to have other people be able to stop it.
That's right. Some kind of friction. Yes, I like that way of thinking about it.
And so coming back to what generally intelligent does. So how does it, tell us about
what's our approach? Yeah. So we basically evolve a system to solve cognitive milestones of infants sequentially from birth through adulthood. Cool. So kind of sequentially increasing in complexity. That is the oversimplified way of describing what we do. Slightly more complex. A slightly more complex way of describing it is we basically, the way that we think about the problem, intelligence evolved to solve a particular set of problems, which is the problems that we had to solve evolutionarily to survive. And the way that the intelligence manifests is we develop these like cognitive capabilities in order to be able to solve those problems. We need to be able to figure out, if there's food in one location and water in a different location, how can we access both the food and the water without dying of hunger or thirst? If there are predators, how do we avoid the predators but still be able to get the thing that we want? It's a complex kind of like natural ecosystem. And so we develop all these cognitive milestones. And a way to think about our approach is it's a little bit like test-driven development, where we start with a simpler set of milestones, cognitive milestones, so kind of like earlier evolutionary. And then we add a slightly more, we develop a system to solve that. We add a slightly more complex milestone, update the system to solve that. If it's not solving it, we can be like, okay, well, why is it solving these but not this next one? So that's kind of the high level. And
that makes sense.
It's really great. It allows us to make progress on solving milestones because it's hard to get stuck when you're like, okay, I have a working subsystem and I just want to figure out how to get the next thing.
Yeah.
And so it's a little bit like evolution in that sense, where like evolution always had a working subsystem.
Yeah, that's interesting. I guess it's like, and so you want to have evolution just didn't get to where we are now. It's like, okay, or like we didn't get to where we are now, being like 30-year-olds or whatever. We were 0 years old and 1 year old before we were here. And so you can say like, hey, AI, can you like do object permanence?
Yes.
Or like, what's an example of a thing that you have it do?
Object permanence is a really good classic one because machine learning systems today have a lot of trouble with object permanence. Or at least in the last few years.
Okay.
There's also a lot of things. There are a lot of other things like learning from other agents, like object solidity, the idea that objects are solid, the idea that objects are continuous, all this like object interaction, how to make trade-offs between different needs. There are like a whole bunch of other things that humans are able to do and animals are able to do that machines aren't necessarily that good at.
Yeah. How far into it are you? Like, are you at age 4 now, or like are we at age 1?
4, we'd have general intelligence.
Okay, sweet. Okay,
So,
yes, okay.
Yeah.
So you're like 2 months or something.
Yeah. So actually, in the first few months of life, the way that developmental psychologists evaluate a baby is they look at what are the how long does it's called looking time paradigm of evaluating what babies understand. They look at how long do babies look at a thing? So, for example, maybe around 3 months old, you learn that objects are solid. And so you can show a baby who's 3 months old a video of 2 objects that just bounce off each other versus a video of 2 objects that pass through each other. And the baby will be, if they're 3, 4, 5, 6 months old, they'll like stare at the one with the objects that pass through each other for a long time because they're like, what happened? That violated my expectations. Whereas like a 2-month-old, they might look at them both for the same amount of time because they're like, I don't know. They're not predicting that objects should not pass through each other. So this is kind of the like violation of expectation paradigm of evaluating whether babies understand things. And this happens in the first 7-8 months of life because babies aren't able to really do other things. So it's hard to test what they understand.
It's only where they're head at and how long they're looking at the thing.
Exactly. Exactly. So our initial setup was, our first set of milestones was, can we learn all of the object understanding, object representations, object permanence, the like understanding that babies learn in the first maybe 6 to 9 months of life, using this violation of expectations paradigm. So we set up and learn that in a fully self-supervised way. So you don't have to give the baby any labels. Babies mostly just look around and then try to kind of understand things for themselves. They do look at what caretakers are doing and copy them, but we can talk about that later. It's more complex. So we ended up developing a system that, like, very simple, very small network that in a fully self-supervised way could learn things like, when the object goes behind the occluder, the object is still behind, the object is still there, even though you can't see it. And so that was kind of the first set of tasks that we set up and solved.
Cool.
Which is cool. Yeah. So now we are moving on to the next set of tasks, which now starts involving the baby interacting with the environment. So we looked at all of the interactions that babies have with the environment. It turns out that babies actually are not very good at doing things in the environment. So we are also looking at all the things that chimpanzees can do in an environment. So that, like, grasp things, eat things, navigate, move, climb. There's really just a few kind of building block things that chimpanzees are able to do that kind of allow them to do a lot of other things. And so we're actually submitting a paper to NeurIPS that is basically in a simulated environment, procedurally generated simulated environment that allows us to be able to set up a ton of skills and test those skills. So what we want is for the same model or agent to be able to do all of these different skills and learn to do them in this environment. And are you able to, and you call that benchmark or something? Is that what you call it? Benchmark?
Yeah. Are you able to show, can we look at can we show the viewers the little image of it?
It's not final.
It's not final, but it's kind of a cool, and see if you can,
You know, you've got like, you know, a little, at the moment it's a monkey, but that's not what the agent's going to end up looking like.
I love it. I think that this is such, and the reason why this, I mean, this was really helpful, and thank you for showing it to the viewers. That's a sneak peek of NeurIPS 2022 or 2023.
Well,
Maybe I know. Fingers crossed. Well, so just to pop a lot of that stuff back off the stack. First, learning about it's kind of like the only training data you can get from babies is just like what they're looking at, and so you don't have any other kind of things that let you know.
Yeah, it's kind of like, how do you set up an evaluation for what a thing knows?
Exactly, and you're trying to like understand. And I just had just thinking about like the Bayesian brain, and I had this guy Carl Friston on my podcast recently, and predictive processing and all that stuff, and so it just makes me think of, for you, kind of what, like, it sounds like to me, and I didn't know when this happens, but our brains get built with all these priors, and the question is, when we're at birth, we start to build them up. And so we start to make these predictions about the world. And then when you're 3 months or 6 months, whatever you said, when we have a prior that says objects should hit each other, but then actually they go through each other, then our brain's like, no, that's bad. And so, do you see what I'm saying?
I do, but I'm not sure I'm not sure how it works exactly. I think what you're saying is potentially we're born with some prior about objects.
No.
We're born with some prior about doing predictions.
We have these meta priors, which our brains do not have essentially any priors when we're born, but then we slowly, and I don't know this that well, but then we slowly start to build out these priors as we're encountering the world. And one of those priors ends up being that objects should hit each other.
That's right. Objects are solid.
The objects are solid.
Many objects are solid. Exactly. Yes. And the way, at least in machine learning, in self-supervised learning, the way that it works is you basically try to predict the future.
Yes.
And then if the future is different than your prediction, you update the way that you predict.
Exactly.
And then eventually you'll learn these kind of underlying principles like, oh, if I have this, then, or, it's obviously not so... not
simple,
so solid as
solid.
Reductive
Exactly.
Reductionist, that's what I'm saying. But you might learn things about objects, you might learn things about materials, you might learn things about colors.
Yep. And so
that help you make the prediction.
Yeah, and it's interesting because it's just like, and it's like, that is our brains being these like Bayesian machines, and then the AI is also this Bayesian machine that just has, in the end, like, correct me if I'm wrong, but like the output state after you were like, oh, it's done the correct thing where it can do what the baby did up to 9 months. What you have is what do you have then? Do you have like a kind of an AI that when you give it certain tasks, it does them in the way that you'd expect? Do you have can you actually look at its kind of like Bayesian priors, or like it's like model?
So the way I would think about it is what you want, or what you get when you feed a system like this that's trying to predict the future, a whole bunch of data, like video. You feed it video, and it develops what we call representations. It's kind of like just a bunch of numbers in a matrix, a bunch of vectors. And these representations the way the model works is you give it frames of video, and then it kind of compresses each frame into a smaller set of numbers, representation. And then...
Do you do that with a convolution? Let's see if this thing... okay, we're still rolling.
It still works.
Yeah.
Do you do it with convolutional neural net?
Yeah, do you do it with convolutional neural net?
We don't. We use a variational autoencoder.
Oh, right, and I learned about that as well, and they seemed kind of similar to me, but we don't need to go into the and we don't need to go into the differences. But you take the big n-dimensional thing, or not n-dimensional, but x by x thing, and you collapse into a 1 by n kind of thing, and you shove that thing into the into like a or into, maybe are you using transformers, or what are you using?
I can explain the architecture. So a type of architecture you might use is you want to take the real world, or in this case, like full pixel frames of video, and then turn it into this like more abstract representation.
Okay.
Compression.
Yeah.
And then you want to take the compressed abstract thing and predict future compressed abstract things of future frames of video.
Yeah. Okay.
That's kind of the setup.
Yeah.
And so to do the compression, the variational autoencoder actually, what it does is it kind of forces the video through this compression, and then forces it back out to try to make it reproduce itself. And so it kind of, trains a compression that's able to make frames of video reproduce itself. And then to predict future, what we call latents, this representation, you can use really any sequence-to-sequence model. You can use RNNs, you can use transformers. A version we ended up with is using a transformer, but a really small one. And they're, works well.
Okay, so if I understand that correctly, yeah, exactly. So, and thank you for the good explanation. And it's like, you have your like video, aka for now, let's just pretend it's an image. You take the image, you crunch it into a 1x(n) space, which you would call a vector if you wanted to, and then you could maybe, and then you put that thing. That's it's latent, aka this thing you don't really care about. That's the in between black box space, and then so you've done the encoding, and then you do the decoding.
That's right.
And then it makes this other image, and at the beginning it was a cat, and at the end you got a dog. So you're like, no, bad AI.
Bad latent.
Bad latent. Yeah. Exactly. And so then what you do is it works on those until the thing at the beginning matches the thing at the end.
That's right.
And then you said this final bit, which was any kind of parameter or sequence to sequence thing. Tell me about that and how you
So basically, in predictive processing, or in a lot of our theories about the brain, one theory is we make predictions about the future. Then when the future actually happens, we kind of like update some stuff.
Yeah.
And then that allows us to make more accurate predictions in the future. And in this machine learning system, you could have something kind of like that, where you are passing in these frames of video. And based on the past frames that you've seen, you now have this latent, and you can pass this latent basically as an input to your next step, your next frame. And so using the past latents that you've seen, you kind of want to create a new latent, and then you, in order to train the model, you want to minimize the difference between the new latent you're predicting and the new true latent. So basically, in the next time step or in some future time step, you would compare your predicted latent against the encode. You pass that frame through the encoder to produce a true latent.
Yes, the second latent.
The second latent. So that's the true latent of that frame of video. Versus your predicted latent, then you try to minimize the distance between the two.
Okay, great.
Yeah.
That makes some sense. And I guess that in the end, what you get is a thing that's both good at it creating latents that are good at representing itself or whatever, where you have the thing and then the latent's good at being like, hey, you can decode stuff or you can encode stuff and you can decode stuff. And then that same latent should also be good at predicting the future, aka you have a given. Those feel almost like two different tasks.
They are. Okay, so the latent doesn't do all of the work. The latent is just a representation of the world.
Yeah.
So it's like, what's an analogy in a person? It's like how you understand what is in, kind of like you're kind of like building blocks.
Yeah, it's almost like your categories, your concepts or something you're taking.
Your beliefs. And so there is information in the in the encoder, and there's also information in the predictor, in the weights of the predictor.
Got it. Yeah, I think that makes sense. And thank you for going down the rabbit hole for a second, because it helps understand. I guess the final piece is you have to, when you're doing the sequence to sequence thing, then what you're doing is you're training it, and you're saying, hey, here's a bunch of video, and you have these latents. And what you say, hey, when you receive latent 1, the next latent was this latent 2. And so you train it, and so that it gets good at making these predictions.
It gets good at predicting its own future, basically. Yeah.
And then once it can predict it, so those predictions are held. If the latent is the categories, or like the concepts, or this one-dimensional vector, the predictions are like held in the transformer or something? Or did you see? It's probably a dumb question. But
No, it's not a dumb question. I think what you're asking is, like, how does it predict the future? Like, what is the algorithm it uses to figure out what will happen in the future?
Yeah, and I know kind of maybe like I know that there's the latent 1 and then the latent 2, and you give it a bunch of data that shows, hey, here's all these latents after each other, so it can kind of learn how the latents kind of connect.
Yeah, so kind of maybe a way to think about it is it's like given a combination of the current state of the world, and like and the weights of this transformer or RNN.
Yeah.
That combination allows us to determine what a future state of the world might be. So it's kind of like, you know, a way to think about the transformer, what it's doing here. It's kind of like a state transition.
Yeah.
Like, how do you transition from this state to a different state?
Yeah,
That's like
cool.
the weights.
That's a good way to explain transformers. And I think that it is, it's like you have, okay, and let me maybe ask one other question here, which is does the transformer, is the thing that the transformer is taking as input, is it because when I imagine transformers generally, you have it's like you're giving it a sequence of text, you know, and then you're like, okay, you said she earlier, and so then when you say it was him and her, you're going to say her because it like looks backwards or whatever. So you're giving it the text, and it's good at the NLP and that kind of stuff. In this reality, it seems like what the transformer is taking as input is the latents?
Yes.
Okay,
So instead of text, you're getting a sequence of latents.
Yeah, okay.
Yeah.
Which in my mind is like roughly equal to these like categories or concepts where you're almost, and this is me just being pilled by Friston recently, where you're taking as input a continuous, it's technically not continuous because it's a bunch of these pixels, but you're taking a continuous sensory state, and then you're collapsing that continuous sensory state into these categories or concepts, the latent, whether you want, and then you are, and then you're pushing that latent through the transformer, and then the transformer is like, okay, great. These categories, when you have a category here, aka solid thing, and you have another category here, solid thing, if they're getting closer and closer and closer, they're probably not going to go through each other. And like the latent would hold that.
Yeah.
Or the transformer would hold that.
I think...
Rip, I didn't get it.
No.
Yeah.
Your explanation is totally valid.
Okay.
And it is the case that in human thinking, it seems like there are continuous kind of like continuous sensory input.
Yeah.
And there are these like discrete linguistic, conceptual, symbolic categories.
Yes.
So I'll call those symbols. They're discrete.
Yeah.
And the world is continuous.
Yeah.
And so like in a human, you know, when I feel a vibe of something, that's like my me processing the continuous state, but it's like illegible because I can't turn that vibe into words yet. So that's like not yet discrete. I think here, the latents are still continuous. Like they're not symbolic in the way that humans interact with symbols. And so I don't want to be misleading on that. That's like the Carl Friston model is a somewhat higher level model of like, okay, well, you have some continuous state, and you know, humans have some process for turning continuous things into discrete symbolic things, and that process is really useful because when you have discrete things, you can do error correction, you can like build them on top of each other, and so like that is important. But here in this model, we are still just dealing with continuous state, and I think it's a difficult, or maybe not difficult, but at least not currently solved problem to figure out, okay, how in neural networks do we combine this continuous state and like discrete symbols, and how do we map symbols to like continuous state.
That makes sense. I think, and I agree, and that's why we made this trick earlier, or the thing to make it easier for Rhys to understand, which is / listeners, which is the latent, which is this one-dimensional vector. Oh, just pretend it's some concepts and some and actually, well, it's not.
Actually not.
It's a big old series of numbers. It's a big old blob, and but
there's information in the blob.
There's information in the blob, and I don't know. I mean, I guess these get to questions around like, so there's information in the blob and so okay, that makes sense. Let's zoom out for 1 second, and I want to note about the benchmark model, which I think is actually really smart, which is so what you're doing is you're setting up a simple environment simpler environment, and then letting the AI learn in that simpler environment, right?
Yes. I would say, I would say it this way, which is we really believe in You know, the field is producing tons of solutions.
Yeah.
So architecture is of various sorts, solving various problems, and like that's awesome.
Mm-hmm.
I really appreciate that. We think that it's quite important to think about the problems to solve, because, you know, intelligence evolved to solve a specific set of problems.
Yeah.
What were those problems? Maybe we should try to solve those problems.
Yeah.
And so we think a lot about kind of what tasks are we trying to actually solve. You know, obviously, you know, to us, ImageNet is not the right task. Classification is not the right task. It's too simplistic. So, you know, for us, we built this environment in order to be able to express a very wide variety of tasks that are quite similar to the tasks necessary for human intelligence. And let's see, how would I, and your question was...
I guess, so I agree with what you're saying, which is there's a version of, I said, oh, you made a simple environment. And you were like, whoa, homie, it's not simple. It is a specific set of problems that we're actually interested in solving.
That's right. And actually, the environment design problem is actually really important. Yeah. Because it is actually really, there are lots of simple environments. And those environments don't lead to intelligence. There are a variety of reasons why. Maybe, you know, like, I think it's still an open question as to basically what is the minimal viable environment necessary for intelligence. And I think some people think like, oh, this environment needs realistic physics, like perfectly realistic physics. And I'm like, I don't think you need perfectly realistic physics to develop intelligence. Like, you know, it seems like that's probably not fully necessary. And so, you know, other people may say, oh, you need completely photorealism. And, you know, I'm currently of the mind, and I could be wrong about all of these things. I might change my mind in 6 months based on what we discover, but I currently don't think you necessarily need fully.
You could have, like, if you took off your glasses, it's like, you still kind of get what's happening in the world.
Exactly. You know? You can be blind and understand what's going on.
Yes.
And so the question here really about the environment is, what is the minimum viable environment that allows us to get intelligence? And my current suspicion is that it has something to do with being forced to make trade-offs, and also these kind of like many different levels of complexity that the world works at. You know, you can break things apart indefinitely and construct them indefinitely in different ways. And maybe that allows for something important. You know, there's a lot of work in object segmentation in machine learning, and one problem with object segmentation is when we think about objects as humans, an object may be an object, but inside the object there are more objects. So, for example, like I'm looking, I'm looking at your computer, and this computer has a keyboard on it, and each key is also an object. So, who's to say that the computer is the object and not the keys? And we have this kind of like fractal zoom. And so it really depends on what level we're paying attention to. You know, a molecule might be an object if we care about that level. So maybe that's important. I'm not sure. And so, you know, we're not really sure exactly what the minimal viable environment is. If any listeners, if this is your line of work, I would love to hear from you because that is a lot of the work. And then we design things to solve the environment.
And I think, and the reason why I just want to emphasize it, because I think it's such a crucial, thinking from this replicator perspective, it's like genes are an answer to the environment. The environment produces a puzzle and says, hey, can anything live near a deep sea vent? And then genes are like, no, I'm trying. Oh, me, I can live here. And then you're like, oh, but here's another puzzle. Can you live in the air? You know, now that you're animals, and then birds eventually flap up and go, I can live in the air. And so, and similarly, all of our memes are similar kind of answers to the environment. It's like you need a way to trust people in cities. As we got the agricultural revolution, it's like religions came around. We're like, hey, what if we had this answer that said that people should be nice to each other, else they go to hell? You know, it's like, okay, that's a pretty good answer for that question. And so I think the question of environment design, I think, is really important, and minimal viable environment seems important. And I think it is, I guess, when I imagine the output of all of your research and work, this version of it, it's like, you'll get these things, kind of like that monkey that we looked at earlier, where you're starting to design a bunch of different environments, and then you start to see a thing in there that looks kind of AGI-ish or whatever. You know, sorry. When I say AGI, I mean there's a whole range of things. You look at something in there and you're like, this is an active agent that is
it's learned to do a bunch of things.
Learned to do a bunch of different things given its environment. Exactly. It's able to. So,
it's like learned about different types of food that it can interact with, and how to like get get the coconut cracked, and how to get something out of a tube, and how to open doors, and a variety of different things.
And let me ask you a question about that, because I think it's something also that, again, kind of from the Friston perspective, you're kind of like, we have this big data version of things, but we also have this like version of things where we got the robot that does its thing. But then if you like chop off, like if you have a dog and that dog, its leg is trapped under a rock, it will eventually like bite off its leg, whatever, in order to like survive, to like go off and like be in the world. But if you like had the Mars rover, and I feel like, didn't this happen where the Mars rover was like trapped under a rock, whatever, it had no idea what to do. So there's this like question of how lots of our AIs these days, or just like machine learning things, are like kind of almost stationary in a sense. They're there, they're chilling, they take in all the data, and then boom, you get ImageNet and good classification things. Your version of things, it has some amount of activeness in it, and that's almost what, at 9 months, once you get into the next stage of what babies can do and what chimps can do, they can do grasping, and they can do all these things. So how do you think about the like active state of like, not only should you learn how the world, what's happening with the world, but you should also be able to actively change it in order to like fit your priors or whatever.
Yeah, I think maybe the way I would think about this is in this dog example that you gave, where the dog was chewing off its own leg, what it was able to do is it was able to modify itself in order to solve the problem. And so it could modify its own limbs to be able to like get rid of its leg. Maybe this is not what you're pointing at, but at the moment, like models don't modify themselves. Now, in reinforcement learning, which is what we do, the model is able to take actions. And there's an action space that's provided to the model. In humans, one action that we're able to take is self-modify. We can change our mind. We can chop off our arm. We can look at a thought and be like, that's weird. That's not right. Let's change that thought. So those are all available actions. In machine learning systems today, the action space is very limited. And so they're not able to self-modify in the same way. They can only really modify based on their inputs, their training data. And so this is a thing that is missing. One thing that we do, at least, is we give the agent proprioceptive data. So that's like your own sensory idea of where all your limbs are and stuff like that. Partly because humans have proprioception. We have this phenomenon called efference copy, where we make an internal copy of all of the signals that go out into our limbs, motor signals. And some, hypotheses, maybe this internal copy allows us to be able to like actually use those signals so that we can predict what's going to happen in the future. So we do give our agent proprioceptive information, but at the moment we don't allow it to like, one action is not modify its own state. But one thing that it can do is it can actually, one way in which it can modify itself, which existing like non-reinforcement learning systems, they don't do, is it can figure out like what to learn more about. So it can control its input data in that way.
Because that's, and that's kind of what I'm pointing at. And mostly I'm just pilled into this recent Carl Friston thing. And so I just think
Carl Friston's awesome.
It's so good. Oh my God. And so I think it's just like this idea of like how to balance, epistemic foraging, aka you're an agent in your environment. You want to maximize your own Bayesian model evidence, aka the evidence that you exist in the world. And so you're looking at stuff, and part of that is like exploiting your current environment where you're eating the bananas there. But part of it is being like, I need to go find out like where the bananas at, like how to create banana trees and all those kinds of things. So I think that gets at it, which I think, I don't know, there's just a sense in which, and we should transition, a sense in which your agents have this kind. I think it's just powerful to make the agents be in a world, because then they get some kind of activeness or in their world, which I think is crucial for intelligence.
Plausibly,
Maybe,
plausibly, I think that's possible, quite possible. That's there's some of the other pieces of it, like the way I describe our problem is we work on self-supervised model-based reinforcement learning.
Okay.
Which means we self-supervised means the environment does not provide the reward signal. And I think you can have agents that are active, where they get like, play Atari games, but they get the signal directly from the environment, the reward directly from the environment, and they get maybe what's called a dense reward. Like they always know if they're getting closer or farther, or even if they get a sparse reward from the environment, like that feels very hard-coded. It's hard for this agent to like choose to change its own goals. The agent doesn't set its own goals.
Yeah.
And I think something that we're kind of interested in understanding is like, it seems like the agent being able to set its own goals and make trade-offs and make decisions and decide what to do, that seemed necessary for being able to develop intelligence.
Yeah.
That said, I think like a part of intelligence is developing good representations about the world and how it works. These large models do a very good job of that.
They got that unlocked.
So I think, we can use representations developed by these large models to be able to bootstrap these agents. But yeah, I agree with you in that. Like
active stuff.
You do want to be able to take actions. It is scarier.
Oh god. Yeah.
So we have to be quite careful about that.
Yes.
Yeah.
Let's transition to that side of things. And I think one side of this is let's just explore this weird replicators frame for a second. I just kind of want to get your hot take on it, which is if we have these genes which are the answers to the environment and they made the tree of life, and then the memes make the tree of ideas and technology, and they are their own answer to the environment. And both those things replicate in the sense that genes make these vehicles, aka us, and then we get more of them, and then for long there's all genes all over the world. And similarly, memes are really good at replicating from mind to mind, and now you have all these, we are the vehicles for Christianity or for capitalism or all these things. But the thing that I don't know is like, it feels... Now we have artificial intelligence, and so I'm not sure if it counts as a third replicator. And maybe, and the reason why it might count these like Temes or something is that you have information that's being, so one piece is that, I don't know if like the internet itself counts, because the internet is just kind of, it's like sending these bits all around the world, and those bits still live in our brains. They're still in our like homes here. And so it feels almost like that's just like a bits version of memes, just kind of like how like the printing press it would still need to live in our brains. But now we have different kinds of things. Kind of like back to the concepts idea that we were talking about earlier. It's like that latent, that vector is a thing that simply doesn't fit in our brains, but is still an evolutionarily found thing that might replicate and might convergently evolve in the environment. So I don't know. What do you think about third replicator stuff?
Yeah. Okay. There are several ways that we can go with this. Maybe we'll go down all the paths.
Okay. Ooh, I'm excited. Can I actually turn on the light?
Definitely.
Let there be light. All right. Okay.
Nice.
So,
several paths we can go down. So one path kind of like rejects the frame from genes and memes, like a gene and meme centric frame.
Yeah.
And one path embraces it.
Okay, let's do both.
Let's embrace it first.
Okay. Nice.
Okay. So this idea is from my co-founder Josh Albrecht, who was extraordinarily brilliant.
Yeah, Josh is
cool. I don't want to take credit for it.
Yeah.
But it's really interesting. So, would you go through a teleporter?
Woof. I would have to. I would have to know that many people were able to go through it and that it was okay.
No,
and all
it's
these
safe.
Things.
It's safe.
Yeah.
Are you sure though? Because like, imagine that you step through this teleporter. You get reconstructed on the other side.
Do I know where I'm going?
You know where you're going. Yeah,
okay.
yeah. And you get reconstructed on the other side.
Yeah.
You're totally safe on the other side. However, what happens to this physical body is it gets shredded through a cheese grater.
Oh, yeah. This is kind of like the ship of. I don't know. Well, would I do that? I would have to go to therapy before and like check in with my sense of self and like all those kind of things. Cause like, I feel sad for the old version of myself that got cheese grated.
That's right. And so this is a question of like, what is self?
Yeah.
What am I as a physical being?
Yeah.
Can I actually replicate myself in this way through a teleporter? Also, maybe there's another variant where you go through a teleporter, but your current self still remains. Well,
yeah. Ooh,
okay,
God, that one is
weird.
weirder.
That's super weird.
Weirder.
Okay,
Yeah.
So teleporters are weird. I would not go through a teleporter because my sense of self is this kind of like physical continuity.
Yeah.
And that kind of makes sense. I'm a physical being.
Yeah.
Like everything about me is physical. One thing that's really weird about general intelligence, AGIs, is that they are not physical beings. They are digital beings.
Yeah.
If you said, I'm willing to step through a teleporter, as a physical being, what you're kind of saying is like the thing that matters is how information similar the thing on the other side is to me, but I actually don't care about continuity, which is weird as a physical being. Like physical beings are like it causes all of these weird, like the cheese grater problem, or the like, what if your current self didn't get destroyed problem. Also, like, are you okay with destroying your current self? That's also weird. So the continuity question is important for physical beings. And but these digital beings are not the same. For them, they can replicate themselves as many times as they want. They can just copy themselves. Continuity actually doesn't make sense as kind of like a sense of self for them. For them, information similarity actually does seem like the right thing. It's like, how similar is this other system to you? That's kind of like how related it is to you. And so I think one thing, like one path to go down with this replicators idea is, I think of digital beings as being different than physical beings. And in fact, like uploading seems quite bad in the sense that like you take a physical being and you make it into a digital being, but it has all this like legacy desire for continuity, and that seems bad. Similarly, like making a digital being have desire for continuity is bad. Like that is just going to introduce all sorts of traumatic, like really morally weird situations. And so, these digital beings are actually like fundamentally different like classes of thing. Where us like what it is or what itself is kind of the information it contains, or the information patterns it contains.
That's interesting, because I think it makes me think of like, we developed the notion, the concept of self, because it was a simple explanation to explain our physical world, which is like, it seems like there's this body that is me and is doing this thing, and when I do this, it's like it's me doing that, and it's not you doing that, it's me. And so we get the self there.
Right. And there's a really good an explanation I like from Anil Seth. He's a studies consciousness, is a professor. He said there's a theory that the reason why we develop our sense of self is because we're physical. If you chop off my arm and I don't know that it's my arm, then I die. That's really bad. So I need to know, like, these are my limbs. And I can't lose them. It's bad if I lose them. And so I kind of develop my sense of self because I'm constantly computing what is part of me, what is not part of me.
Because then should I help it? Or exactly. And then, but as you said, there's this weird thing. And I see what you're saying with the digital beings thing, which is that because the way bits work, and because you can copy them and duplicate them all around the world all for free, this idea that there is a self, that you'd have this like little set of like, oh, here's like a picture of my grandma, and then I copy it and send it over there. It's like, no, there's like those two pictures. Did the first one have a sense of self, and now the second one is over here? And it's like, and so I think that understanding how these AGIs will develop, if and how they develop. I see what you're saying.
Like,
Just,
they may not have the same kind of self, right? They don't need to compute what is part of them. Totally.
Well, they might. What they'll want to do, I think, is that there will be aggregations of them, informational aggregations that are able to self-perpetuate, and that those things, they might be able to just copy themselves. But there might be like, I don't know, as the I guess some of the questions here are like, what does the environment look like, and how much are they able to copy themselves? In theory, they're able to copy themselves infinitely. Is this so this was, you said you were going to go two directions with this. One direction was the like, okay, if we're down the like believing things are replicators thing, then this is where you went, which is like, hey, we have they might be totally separate. They might not even be able to think of themselves as an entity that's trying to replicate, because they're this totally separate thing.
Because they're not trying to replicate.
Yes, totally.
Humans are trying to replicate because we were trying to survive. That was our objective function. For billions of years. But that might not be that might not be true for digital agents. Maybe their survival mechanism is some other entity replicates the ones that accomplish their goals effectively in the way that humans want them to accomplish their goals. Maybe that's, their kind of quote unquote survival function. So then they want to accomplish their goals. And that kind of like, they're not trying to survive at all costs. Hopefully we don't create ones that are trying to survive at all costs. That seems really dangerous. Nobody do that.
Yeah.
So they're not trying to survive at all costs. So maybe they won't develop the same sense of a self, be a desire for replication. If some external thing is replicating ones with certain properties, they'll end up with those properties.
Yeah, that's interesting. Yeah, thinking about some kind of external thing doing the replication instead of the thing itself. Do you think so? That was one path you could have gone. What was the other path?
The other path was So the other path was reject the premise that things are replicators.
Yes. Yeah. Great.
And so in this frame,
there goes my book. You ruined my book, Kanjun.
Oh, no.
Oh my God! I've been working on this thing, and now it's ruined. No, go on.
I haven't read the book yet.
No, you're fine. No, it's not even. It's in process. So this is helpful feedback. Yeah.
Okay. Okay, so let's imagine we reject the premise that things are replicators, and instead of thinking of genes and memes as replicators, we think of why are there genes and why are there memes? And, the way I think about that is, okay, why do we have genes? Earlier I was mentioning this. Something that we do a lot of work on and we're very interested in is network architecture search.
Yeah. What is that?
So it's basically how can you automatically find solutions to the problem setup that you have.
Okay.
Find neural networks that automatically find neural network architectures that can solve your problem.
Got it. I'm reminded of like lottery ticket stuff where you get the lottery ticket, and why can't we get faster at finding the lottery ticket?
Right. Yeah. So like finding a lottery ticket network. That's kind of like in the same realm. Even, honestly, like training a giant transformer is kind of a type of architecture search. You end up changing the architecture to have different weights. But this idea of architecture search is, maybe you can automatically find somewhat different architectures that can solve your problem easily. And so you can think about, when we think about architecture search, one problem we run into is architectures are so complex to describe. And like, if you had to specify the space of all possible architectures, how would you like evolve that space? That's such a huge search space. Same is true with like human biology. Our biology is so complex. If you had to specify every single cell, that's such a huge search space. You can't do that. And so genes are basically a genotype that produces a phenotype, and the search can happen through the genotype. And so for architecture search, potentially one plausible way that you might want to do it is to have a genotype that you can search through that's a smaller search space, and then that produces different phenotypes of architectures. And if I think about like, what is the role of genes? Why do we have DNA? I think we have DNA because it's much more, and I think this is also Josh's idea, so I just want to give him credit for that.
Nice. We
talk all the time.
Exactly. Who knows who created?
Who knows? But I think this is also Josh's idea, so you should definitely read his work.
Apply to work at Generally Intelligent AI maybe. Okay.
So why do we have genes? Well, genes provide a much smaller search space for evolution. So you can easily mutate different genes, which we see happen all the time. And that mutation allows us to end up with all sorts of combinations of phenotypes, some which survive, some which die. And so genes allow evolution to do architecture search. That's why genes exist.
Yeah.
So that's like one way to think about why genes exist. Now, it also has this interesting phenomenon of replicating certain genes, because those are the ones that were fit and those are the ones that survive. But that's not why genes exist. That's kind of like rejecting the premise. Okay, I'm going to reject the premise again for memes. Sorry, you can say
reject the premise for me. So what I'm hearing is, it's not like the genes didn't show up in order to replicate. They showed up in order to be a smaller, do the genotype search instead of the phenotype search for this, because it's hard to do the phenotype search for these larger, more complex spaces. And so you just keep it to a smaller space. Okay. And then for memes, reject the premise for memes.
Reject the premise for memes. Question is, why do we have memes? Like, why do we beliefs spread through the population? You could imagine that we have some alien species that doesn't have memes at all, because they don't copy each other. They don't take beliefs from each other. They derive everything from first principles. That's possible. So There's actually a really interesting book called Darwin's Unfinished Symphony. I think Leyland, guy's first name. And one, thesis that he proposes in this book is they ran some competition. I have not read any of these papers, so I'm not sure exactly. I'm like still in the middle of this book. Yep. They ran some competition to try to understand, I think, why copying behavior develops or something like this. Well, anyway, what they concluded was copying is very efficient. The reason it's efficient is because other animals' behaviors serve as a filter on all possible behaviors. If you had to do all possible behaviors, then it's very inefficient. You have to search through behavior space yourself. Instead, you could copy other animal behaviors, and that now reduces your potential search space. Yeah. So again, memes are a search space reduction mechanism. Yep. That makes you efficiently take behaviors that allow you to survive. Yep. And so it's actually, I think he ran there's some mathematical model he ran maybe that discovered that most species most organisms tend toward copying. And it's interesting, you do see copying everywhere. In bees, in mice, in birds, in primates, in name an animal, they copy. They copy behaviors from other animals. So memes, what are memes? Oh, it's us copying other people's beliefs.
Yeah, that makes sense. I think that there's a similar version of that for genes too, which is that a gene, if you were it's like if you are trying to balance, explore, exploit, what you do is you're just like, oh man, let's just keep whatever worked last time. Like that organism seemed to be fine. Let's just roll it back. Let's just do the same thing and copy it. And similarly, if you're trying to find in mimetic space and you're like, what those people are doing is probably fine. Let's just do the same thing. That's they right. seem and to exist.
The unfit ones, the unfit memes will die out. Similarly, the unfit genes will die out.
Yeah. So I think we can transition to the final bit of this. But I hear what you're saying here, which is that to think about, I guess on the memes, on the gene side, it's like, okay, think about the genotype versus phenotype and how to just the state or the search spaces and whether or not replication is necessarily this necessary convergently evolved thing, or whether there is some kind of it would just evolve for this other reason and then it just happened to, I don't know, but that's because then you will see stuff. I think you have to get replication within these systems because the things that persist are the things that want to access energy and want to replicate.
Yeah, so here's how I'd frame it.
Yeah.
Framing it as these are the things that want to replicate gives the thing itself a lot of agency.
Yeah, classic.
And so it's a framing around the gene taking actions in order to replicate itself, which it doesn't.
Yeah.
Whereas I think my reject the premise frame is I'm looking at what behavior the system is causing. So the frame is from the system as opposed to from the gene. And
that's coffee.
So,
you're good.
So, in the replicator framing, you're
you can have
drink some water.
Yes, 100%. And as you do that, let me actually...
I think I inhaled some dust.
Yeah, you're good. Okay, great. Okay, sweet. Okay,
let me try that again.
Yeah, great.
Yeah, so basically the reject the premise is in the replicator frame, you're looking from the perspective of the gene or the meme, and you're saying this thing wants to replicate, but it doesn't want to. Instead, what I'm saying is if you look from the perspective of the overall system, what the system has done is set up a system such that particular things do replicate. And so it's not like the ones that quote unquote want to replicate are the ones that replicate. No, instead the ones that are fit according to the standards of the system are the ones that end up getting replicated. If the system changes, different things will get replicated. So different memes will get replicated in a different system. Similarly, different genes get replicated in different ecosystems that select for different things. So,
yeah, I think it's from the perspective of the environment or the system, you're looking down, you're like, okay, what can survive here? And as you said, you could imagine certain versions of things where replication doesn't emerge there, where it's like, I just think my main takeaway here is that, like, I think seeing the world from the frame of the replicators is good, but also a thing that humans don't often do is like zooming way out and seeing the frame from the perspective of like the environment.
That's
like,
right.
You know, it's like as long as you do both those things.
I think maybe what I'm saying is there is no frame from the perspective of the replicators. Like replicators don't have a desire to replicate. There's no such thing as a desire. Instead, you look from the frame of the environment and you're like, okay, there is this phenomenon of replication.
Yeah.
And there are these attributes that cause this phenomenon of replication.
Yes.
And this phenomenon is true. It does occur.
Yes.
And it's possible. Maybe in all systems there is a replication phenomenon of some sort.
Yeah. No, I like that. I think it's a classic, like, you know, in Dawkins' self-esteem, where he's like, yeah, I'm saying they want to replicate, but really it's just saying the things that eventually only exist are the ones that have this, we're able to capture energy from the environment or whatever and perpetuate. And so that's kind of like the systems view. Okay, so let's start to get into wrap mode. And I think that, well, let me think if there's any. So yeah, y'all are building this.
Well, before we go into wrap mode, I want to ask you, like, is that was this what you were hoping for? Was this interesting? Or, sorry, maybe a different question is, what are your objections to this?
To that framing?
The
systems framing?
Systems framing? And also the digital being framing.
Yeah, okay, I can answer both those. And thank you for having me respond. I think the digital beings framing, that one's interesting. And I think that gets at, there's something really weird about, I think, so a couple of responses. A is like this like Markov blankets version thing, which is like this Friston thing that says Markov blankets are what defines a thing from its environment. And so
that's interesting.
It's like a statistical representation that is used to do that.
Well, it's actually Markov blanket is like in a graph, in like a connected graph. It basically says like conditioned on these nodes, these other nodes are independent from each other. Yeah. And so I can see how it's kind of like a separation.
The independent from each other kind of thing.
From each other, but then you would have to model the world and people as graphs. Question mark? I guess you could.
I think you. Well, yeah. So, and I think So that frame, and whether we use the mathematical formalism of Markov blankets, this idea that things desire, quote unquote, that replicators, if we keep the replicators desire framing, or you could do the systems view, which is that things will develop containers, and the lipid layers at the early. With early life, or with us having our bodies with our skin on the outside, and also with memes and having these kind of like there are people where the Republicans versus the Democrats or whatever. It's like this is like like the tendency towards groups and towards containers is a thing that occurs.
That's interesting.
I think it's kind of and so I think that what you said is like, hey, we might have these things that don't containerize. Which is that you have this thing that has no sense of self, it's here and the same JPEG is over there, the same kind of model is over there. And so can it really have a sense of self given that these other things are just copies of it that are that are infinitely cheap to produce and replicate? And so I think, that's a kind of a square peg round hole thing where it's like, I do think that there's this truth of containerization or Markov blankets convergently evolving. And I think that you have the truth of how computers work and how bits work, and that in transistors, and that you'll have these things where their natural kind of Markov blankets around themselves will not necessarily be traditional, but might be, but I do think, and I think that the containers show up when you're fighting for resources, like you were talking about with your hand, when your hand gets chopped off. The reason why I need to know it's my hand and not yours is because like I need it in order to survive and all these things. Like I should put food in my mouth, not your mouth.
That's interesting. So containers arise when you're fighting for resources.
So I think that, and this is the question of like when you have these, you can imagine, and kind of you can imagine this already happening where it's like all these. There's a state space or a kind of a design space of different. AIs that are looking for Google compute resources, and the ones that are succeeding are the StarCraft one and the AlphaFold one, and the chess one. And so I think maybe so they do containerize in their own way.
That's interesting. Yeah, maybe a question to ask is like, it certainly seems like maybe this containerization phenomenon would happen with neural networks. Yeah. So the question might be like, what resources might it fight over such that it ends up like grouping like groups end up forming, and so what groups might form as a result of those resources that is fighting over.
That, yeah, exactly.
Compute is interesting.
I think, because what are they fighting for? It's like...
Yeah, more compute equals more performance.
Yeah.
So I could see that. Like, if you only replicate the ones that are performing well, then they would want more compute in order to have better performance.
Mm-hmm. And there's kind of there's a weird, like, human-them coevolution here, where it's like, right now, their main space, that their main competitive landscape, fitness landscape, is based off of what we want as well. And so it's like, some of what they're fighting for, too, is like, the space of, like, there's only, if you think about the space of all possible, like, domestic robots, there are going to be ones that do the Roombas, and so there's going to be a battle for Roomba-ness and for cleaning, and there's going to be lots of cute little Roombas, but in the end, they're going to have containers around themselves, because, like, this Roomba wants to beat this other Roomba because it wants to be the one that actually cleans your freaking room, or else it doesn't exist anymore. So I don't know, but I don't know how that totally translates into the world of pure bits. So, because it's easier with atoms, talking about atoms like that. So I don't know about the bits.
It's interesting. Yeah, I mean, so thinking from the systems perspective, it's like, if you have a system that replicates, like where humans replicate the AGIs that achieve their goals, achieve the humans' goals more effectively, then that may select for AGIs that use more compute, or like use compute more efficiently. And so you end up replicating AGIs that use compute efficiently, or use much more compute, or something like that.
Yeah.
It's interesting.
And in theory, hopefully compute aligned with human values or whatever. But yeah, there's a, yeah. And so that's my rough response to your first one. But I think it's interesting, is like the sense of self with these things and where containers show up. On your other one, which is the pushback on which lens you're kind of viewing it from, I'm reminded of, there's Neil Stephenson, but then there's also the other guy, Kim Stanley Robinson. Kim Stanley Robinson's recent book, which I'm going to forget the name of, is... it tells the world from the perspective of lots of different lenses, from the perspective of a photon, perspective of carbon factory, whatever, all these things. And and so I think that what would I say here? I think that there's some kind of yeah, I mean, I do think that, so I agree with you to say that there are one of the main things is that we have environments that then provide puzzles that need to be solved. And that's even before genes and memes, you had like the environment, aka the laws of physics, provided a puzzle, which was what can exist in orbits based off of, we have gravity, we got the strong nuclear force, and we have like electromagnetism, and then we get boom, like stars exist and other orbiting things exist, like planets and stuff, these like blobs and then orbits. And so I think that there's so then thinking about like, so I think that the thinking about what the system or what the environment, like the puzzles that it's giving, I think is really important. And in some ways I agree with you to say that the puzzles are upstream of the desire for replication. Like replication is just a good trick in the design space of, hey, you have these puzzles coming from above. Oh, damn, I want a puzzle good. Like you were saying, it's like, I should probably just replicate what they're doing, or replicate, like the gene should just replicate itself instead of trying to make a whole new body each time. It's like, just do the same thing. So I think that there's a lot of truth there. And I also think that there is again, these fighting over resources in some kind of fitness landscape. It's like if you have some kind of religion, and there was this religion, the spinners, that they didn't missionary, they were all celibate, and they died out within like 25 years. And so, yeah, so I think that upstreamness is important, and the puzzles that are doing is important. I think that replication is a good fit for the kind of puzzles that are produced, and I think that there's a fighting over resources where the things that succeed are the most, are things that get best access to those resources. And yeah.
That's interesting.
What do you think about that?
That's interesting. It's kind of like what you're saying is the phenomenon of replication has properties that make replication happen or something. Or like religions that don't have these replication properties die out,
Yeah.
whereas religions with great viral factor don't die out.
Yeah.
Or like religions, like I think the Mormons have a CRM.
Yes. Oh yeah, the Mormons got CRM.
That's
Oh,
right.
sorry, I said hell yeah. I meant heck yeah. Oh.
They invented the CRM,
Yeah, oh.
is what I've heard.
No, they invented the CRM?
Yeah, like before
Oh.
salespeople used them.
That's amazing.
And then, okay, this is just the story, which
Yeah.
is, and then they hired enterprise salespeople who were Mormons because they're really effective at convincing people.
Yes, and they've done a great job.
And they've done a great job.
Yeah.
I could be wrong.
Yeah. So the things replicate. So I guess I think that replication is a kind of a desire for replication is an emergent behavior based off of these puzzles that the environment sends. So I agree with your perspective, which is to think from the environmental lens.
It's like, and like certain properties make replication more effective. Is that what you're saying?
What I'm saying is that in order to, I guess what I'm saying is that like, in order to things that solve puzzles, the environment gives a puzzle. How can I get light from, or how can I do photosynthesis with the sun? Oh, I'm going to develop photosynthesis, and now I can like get energy from the sun. Those puzzles that are provided, the things that solve them, you could just have like a one-off solving thing. But if something actually exists, has this, existential imperative, it needs to both solve the problem and repeatedly solve the problem in order for us to point at it and say that thing exists.
I think maybe that's interesting. Maybe my environmental framing maybe would be a little bit different, which is that by definition, solving the problem causes the replication. So, for example, animals that are able to, like humans, we're very good at replicating. And we are in an environment where the problem to solve is like food and survival, or like, survival, which breaks down into food and other, like, don't get hunted and don't die.
Food, have sex, don't get hunted.
That's
like
right.
it's simple.
Have sex and don't get hunted.
Yeah.
That's how you survive.
Yeah.
And I guess, okay, so in your point about photosynthesis, everything that didn't figure out photosynthesis was not able to like use this extra resource. And so those things then died out, or, maybe they're just not using this resource. And so we don't see any of those things because they didn't solve this problem of using this resource.
And that if you had a one-off thing, you could imagine something that wasn't doing replication that solved the problem. That was like, I developed photosynthesis. Isn't this sweet?
And if it didn't replicate, then it wouldn't happen.
Then you did it. You technically solved the problem in the environment, but we don't point at you and say you exist because.
So there's still a replication component to it. It's like everything that does survive has to actually try to replicate.
Yeah. In order for us to point at something and say it's an object, it just needs to like.
The weird thing is, though, it feels like genes and memes don't have this property where they're trying to replicate. Like both genes and memes, they end up replicating because of the selection, because of the system selection effects. Whereas organisms do try to replicate. They do things in order to replicate. And so it feels like they're separate in this way. Like a plant does replicate. If it doesn't try to replicate, it dies out. But genes can't try to replicate as far as we can tell.
Yeah, I think this is just like a framing question. I think what I would say is that it's kind of awkward. It's like, so yeah, I think that from a plant, the plant is the thing that is spreading its seed, and then you get more little plants. And
that's like a clear replication action.
Yeah.
Like humans have sex, and then more humans are produced. It's a clear replication action.
Yes.
So in the gene and meme example,
so the gene, I think that what the claim would say, and this is mostly a Dawkins kind of claim, is just like the plant is just a vehicle for the genes, and that the plant it is doing all these actions in the world to make the seeds and stuff, but in the end, there's if you think about all the genes that exist within the plant, some of those genes in there say replicate. They say, again, I'm not really a biologist, but they say, spread your seed, And I think that the ones that didn't say that in the pre-plant days, they went away. And so, yes, the plant has this phenotype of quote unquote replication. But in fact, that
I see what you're
phenotype
saying.
is
It's
coded
encoded in
by
the
the
genes.
genotype. Yeah.
Interesting. So then what that would mean is that any genes that don't like specify the replication behavior of the plant then would be able to die out. So
Yes.
the like non-replication genes would die out.
Yes. And I would say one other thing here, which is, so you see this as, well, A, you see like intense selfish gene action where there's this, I wish I could remember the name, but it's essentially a gene that copies itself within genomes, and it within human genomes, it's like 13% of our genome. It's just like one thing that's just really good at copying itself. It has no other, it does nothing else. And so it's kind of just like exploiting the rest of our thing, just like really good at replicating. So that's kind of an example of like a weird sub-example of this. I think that I was going to say one piece here, which was that the genes are replicating, they have this desire, the genotype has this thing, and the plants, the genes, what I would say is that you can even see this at like a deep down, like biological level, which is that, and this gets into like von Neumann replicators and stuff like that, but like that you have to have, we do DNA transcription where we look at it, we read the thing, and we get all these, our mRNA, our messenger RNA, and that is a copy of the DNA. So we have this copying thing. Like that replication is really crucial. And then we do the building piece where we then do the transcription, then we do the translation, which is push it through the ribosome, the 3D printer, and have it print out new proteins. And so I do think that I'm not sure, you might be able to find alien species that don't have some kind of copying mechanism, or like some kind of like copying the source code and then like reproducing the source code. Like you got to make the machine and you got to put new copies of the machine into itself.
That might just be a physical thing though. Like if I think about computers, I guess if I had some code that specified some phenotype, like some architecture, do I need to copy the code in order to produce the architecture? Not necessarily. I guess computers are copying things all the time, but then they're only stored temporarily, and then they get discarded, and so the copies get discarded, and then the genotype gets produced. So, like we would copy segments of this code, pass it through some function to produce the architecture. Now the architecture is what we wanted, and we're going to train the network, and then we go back in and modify this code and then like try a different architecture and pass it through this function. So I guess in that sense, it's kind of like the 3D printer, but like a lot of the copies are discarded.
Yeah, and there's a weird thing too with like the copies and where the von Neumann thing is like you have to make the machine and you have to put if you want to make a replicator, it has to contain both the instructions for making a new machine and you have to be able to produce it, and you have to be able to put the copy of the like instructions into the new thing. And yeah, I think it's weird with computers, which like we kind of have like the new machine creation is kind of like, well, we already got all these computers around, so you don't really need to make a new machine. You just kind of copy the code and send it to your grandma, and like she receives your JPEG or whatever. So I'm not sure. So yes, I think we should get into rap-ish mode.
Okay.
But this will be an ongoing conversation, and I think maybe as a final, let me just double check my little notes here. Let's finish up with a couple of fun things. First, you're making this. Do you want to talk about the neighborhood at all?
No.
Okay, great.
I don't think so.
Okay, great.
I don't really identify as a community builder.
Okay, that's interesting. I called you a community builder, but I see you as a community builder, but maybe not. Who knows?
That's really interesting.
Come to San Francisco is a TLDR there.
That's right. Okay, we can briefly talk about it. We can talk about the neighborhood and Science Plus.
No. We're good. Check out Kanjun.me to see these other cool things that Kanjun is doing.
That's right. Kanjun.me.
Yeah, and then the other. Let's do a tiny little. Let me ask one question for you, which is, what was the thing that we're going to do? We're going to do a little bit of overrated, underrated, and then a little bit one of the questions. The first one is, what do you think about? There's this great Daniel Gross quote about how the people that are doing cool things in the world are, and not to say that people aren't, but whatever. They had this like little feedback loop set off inside them where they were like, whoa, I have agency, and I can be curious, and I can learn, and I can go and be excited about it and go do things. When in your life did that little thing get catalyzed?
Oh, wow. I think it happened multiple times. I think magnet programs are really important, and it's really sad that people are destroying them.
Yeah.
I was went into a magnet program when I was in 4th grade. They like picked some people from the district and put them in a room together. And in 4th grade was when I realized, like, oh, wow, like there's a different way to school where I'm not just doing what the teacher says, but like I can be curious and understand things and work through all of the books much faster and not be held back. And I just felt like this incredible sense of freedom because of this magnet program. And I think really that speaks to like putting more trust in kids and kids' curiosity. The second one was actually CFAR, Center for Applied Rationality. I went to a CFAR workshop in 2014, and I think CFAR has this like incredible way of injecting agency into people, and in particular, like helping you realize all your problems in your life are solvable. You can solve all of them, every single one, no matter how hard you think it is, like is solvable. And after I realized that, I was like, oh, all my problems are solvable. I'm just going to solve all my problems. So I solved them. Like, you know, that was, those are 2 agency-inducing experiences. And then the third one, I would say, neither of those 2 were feedback loops. They were kind of like single moments in time. The archive, which was this house in San Francisco, that was a crazy agency feedback loop. Where, like, the initial impetus for it was we felt like in college is where people make most of their friends. And my friend Aram, he found a military study where they inspected what led to the closest relationships. And they discovered that there are 3 things. One is shared experiences. One is feeling like you can let your guard down. And the last one is spontaneous interactions. And so we started this just to like be able to, you know, pull people who we wanted to become good friends with. But it ended up becoming this really interesting, I think my other housemate, Jason, called it a self-actualization machine. Someone enter the archive and then like 2 years later feel like self-actualize, like be incredibly different and incredibly self-actualized. And there were a ton of feedback loops that we had, like people always thinking about how to change and solve problems and improve themselves. And, you know, to the point of copying the like norms and the environment around you. I think that was a crazy agency feedback loop.
That's amazing.
Like I wouldn't be doing any of the things I'm doing now.
Totally.
Yeah.
It makes me think it's like, agency begets agency. You like see the other people doing something. Like, okay, we could do stuff.
Yeah, you're like, I can do that too. Wow, why didn't I think of making a list of reflection prompts? The most recent thing that I adopted from one of my friends from the archive.
Yeah, that's great. Cool. And then the other thing that I want to do is overrated, underrated. And so so these are kind of general, but let's start at the general level. AI. Is AI overrated or underrated? 30 seconds.
I don't like these because it's so nuanced.
Yep, too bad.
What is AI? AI in general, I think a lot of things are like we've made more progress in the last 5 years than we've made in the last 60. This field is crazy. It's growing exponentially. The number of good papers is growing exponentially. It's just like crazy. Everything is crazy. So I don't think it's overrated.
Yeah.
It may be underrated. I think general intelligence might happen sooner than most people think.
I saw a lot of people update on their like, hey, heads up that my update towards AGI has actually moved up to 2 years because of Dolly and all these. And it's like, oh boy.
Right. And there's a lot more where that came from. You know, you only see the outside, the external outputs of what's happening. But I think, you know, when talking to everyone,
people on the ground, all the human capital, all that. It's like, wow, this is going to be amazing. Okay, specifically transformers, because our transformers within AI. I read this thing from Andre from Kapworthy or whatever from Tesla, who's like, oh, everybody's just converging on transformers as the main architecture. Are they overrated or underrated?
I think they're underrated in certain ways and overrated in other ways. So I think transformers are a really incredible, very general architecture. And basically, like the transformer doesn't have as many maybe biases or restrictions as other architectures, and it is able to learn these kind of like correlations between things, and it kind of like learns it's like more general, and so you can give it a lot of data and it can adopt the shape of whatever data you give it, and it's really powerful. They are maybe overrated in the sense that I think a lot of people think that just scaling up transformers will get you to general intelligence. And just the computation that's happening in the transformer is missing a bunch of things required for general intelligence. That seems definitely overrated.
Great, got it.
Yeah.
And the final question is, San Francisco. I mean, there was this time I moved here 2 years ago, and then it was like, and obviously COVID happened. Everybody was like, screw San Francisco. And people moved away, and now people move back. What do you think it is? Overrated or underrated?
I think San Francisco is underrated.
Underrated.
Yeah, still underrated. Always, might be for a while. We're starting this neighborhood in San Francisco, and I think what's amazing about San Francisco is that it's this shelling point, and it's just going to become more of a shelling point with the neighborhood. People have moved back from New York for it. I think ultimately, back to feedback loops. And I saw you had a question about what advice I'd have for young people.
Yeah.
Which is, I think, I really become the people around me, and it's, we talked about copying behavior. Copying is really efficient.
Yeah.
And so if you want to grow really fast, copying is the most efficient way to grow in some situations.
Mm-hmm.
Obviously, you want to derive some things from first principles, but so San Francisco is underrated in the sense that it's the only place I've ever seen with this incredibly optimistic view of what people can create in the future and what the future can be and our ability to shape that. And there are tons of people who have incredible amounts of agency doing a lot of different things. I think it has its own problems, both at the city governance level, but it's a very young city, so I think we'll figure that out. But also at a cultural level, maybe we could value intellectual depth instead of hot takes.
More long podcasts. Yeah.
More long podcasts. That's right. That's right.
Beautiful. Well, that I agree, and I do think there's a beautiful being aware of who you're around, the copying behavior, and the shelling point of San Francisco is great. There is this amazing sense of agency here, which is really back to your first question. It's being in the archive is a great place to get agency. And so if you want agency, and you can get it on the internet, which is amazing, and you can get it everywhere, but here's a great place.
That's right.
Beautiful. So with that, thank you so much for coming on the show. Is there a place, a thing that you would recommend? I mean, what I'd recommend to the listeners is, and you can check out kanjun.me, and there is great stuff there around this cool Science++ project and how meta science stuff. And then there's the neighborhood, which is this cool community experiment that's happening. And then also Kanjun is an angel investor, so if you want cash money, hit her up.
That's true.
It just and then you can also go to generallyintelligent.ai, and there's some cool stuff there. Kanjun has a podcast, and so if you want to go deeper on the machine learning side of things, go there. And if
we interview researchers about their work.
Yeah, exactly.
And talk about the technical details of it.
Exactly. So researchers, technical stuff, but then honestly at the I kind of, and Kanjun said not to talk about this today, but the blog posts, I've read some of the blog posts before. They were kind of helpful for a noob like me, where it's okay, here is how this variational encoder works, and you guys have a pretty good, it's clear explanation. So I don't know, I found that to be nice. You can also check out, they're obviously hiring for developers and non-developers,
systems engineers and machine learning research engineers.
Okay, those people. Yeah. So anything else that you would like to say to our listeners, Kanjun?
No,
follow her on Twitter,
you can
I guess.
Follow me on Twitter. Or DM me on Twitter if you want to talk about this stuff. I think a lot about how the mind works also. So that's something we didn't cover. But yeah, we can talk about that.
Hit her up. If you want more agency, hit her up and say, how can I be more agentful? And she'll say, woohoo, thank you, welcome.
I do helping young people. So if you're a young person, feel free to DM me.
Yeah, beautiful. Thank you so much, Kanjun, and goodbye, everybody.
Bye.
Peace, peace, peace. Thanks so much for listening today. If you liked the show, please give us a 5-star podcast review or subscribe on YouTube. And if you'd like to chat about this episode with a community of amazing, smart, ambitious, divergent people, come on by and join our Discord. You can find it at root.co. That's ROOTE.co. And then finally, if you'd like to contribute to these ideas being shared more widely in society, you can support the podcast production team at patreon.com/Rhys Lindmark. That's patreon.com/RHYSLINDMARK. Thanks, and see you here for the next episode. Bye.